Yeah, okay. Yeah, we'll get started. Oh, it's like 1 minute. Yeah, we'll get started in today's Frontier Condensed Matter Physics seminar series that I'm organizing with Tomo Yumura at Columbia. Today, we're actually extremely happy to have Leon Balents. Actually, I know Leon for many years, but mostly, for his work on quantum spin liquid. But he just told me that, his recent focus has shifted to this very exotic exciton, Mott insulators, system that he's going to try to tell us his most recent result on this. Yeah, so Leon, it's all yours.
Great. Thanks, Pengcheng. Well, it's yeah, pleasure to give this talk. I happened to be on the East Coast for a month, so I took this shot last week from it's called the High Line in New York City, a nice shot of Empire State Building. I'm kind of proud of it. Anyway, it's fun to be here. Let's see. No, that's not working. Click. Here we go. But as Pengcheng said, I'm kind of talking about a different topic here. I wouldn't say my focus has really shifted to this, but it's something I got interested in the last year or so, really because of experiments from these guys. Chen-Hao Jin is a assistant professor in the UCSB physics department. It's really his group that's doing the experiments that got us interested in this system, and his student, Richen Zhang, who has discussed a lot with us. And I've been working on this project with two great young scientists. One of them is Tessa Cookmeyer, who's a postdoc at KITP, and Zhenhao Song is my student. The kind of context for this problem goes back a few decades to kind of the late 1980s, when a lot of physicists were thinking about the bosonic analog of the Mott transition. So the Mott transition is this famous transition between a metal and an insulator driven by strong Coulomb repulsion. That's normally we think of that, study that in something like the Hubbard model, which is a Hubbard model of strongly interacting electrons. When people thought about the analog problem for bosons hopping around on a lattice, so Bj is a boson annihilation operator, Bi dagger is a boson creation operator. There's some hopping of bosons on a lattice and some repulsion, so it costs some energy U to put more than one boson on a lattice site. Unlike electrons, you don't have Pauli exclusion, so you could in principle put as many bosons as you want in one single quantum state. This is kind of a model that originally people were thinking about for arrays of very small Josephson junctions, where T would be something like a Josephson coupling between little superconducting islands, and U is something like a charging energy, a capacitive charging energy for a small island. And in this seminal work of Fisher et al. In the late 1980s, they wrote down this kind of phase diagram. Their sort of most important parameter is on this horizontal axis. It's the strength of the hopping. They called it J rather than T, divided by the strength of the interaction, V rather than U. So when J is really large, so the kinetic energy dominates, we have the kind of the usual situation. We expect at low temperatures in a system of bosons that they form a Bose-Einstein condensate. So the Bose-Einstein condensate is kind of a very simple state. You imagine you put every boson into the lowest kinetic energy state, which is just a zero momentum state. And so it's a macroscopic occupation. I have to put a number of bosons equal to the number in the entire system into this one state. In the other limit, kind of on the left-hand side, where the interactions are big or the hopping is small, we can sort of neglect the hopping term and simply I just want to arrange bosons in some way that they don't have they pay the minimum amount of repulsion. And one gets these regions here. This vertical axis is chemical potential, where the boson density locks into fixed numbers. There are regions, these are called Mott insulators, where I have 1, 2, 3, or more bosons per site. And these are kind of incompressible phases. So these are the analog of insulators in electronic systems. This BC is a superfluid state. And they found this very nice phase diagram. That was never really realized that well in the original context of Josephson junction arrays. But in the early 2000s, people were able to realize this very well in ultra-cold atoms by trapping ultra-cold atoms, bosonic atoms, in an optical lattice that would confine these bosons to the minimum of that potential, and you could think of an effective boson-Hubbard model describing the kind of lowest energy states in each well. And they did these beautiful experiments, starting originally with these ones from Marcus Greiner, where they what they probe is actually the momentum distribution of the gas. When so this is an image which you should regard as in momentum space. When the interactions are weak, the bosons all fall into the lowest momentum state. So these they become very concentrated around k equals 0. But as you increase interactions, eventually they form this Mott insulating state, which is not a momentum state, eigenstate at all. It's not a macroscopic occupation. And these images, it looks blurry. And about a decade later, these AMO guys developed these quantum gas microscopes where they could now put these bosons in a lattice and image the locations of the bosons. So while the left image is kind of momentum space image and the right, this is a real space image. And you can see these regions where you have kind of Mott insulating shells that alternate with different amounts of filling. There's a lot of beautiful physics studied there. So this is kind of an example. These two phases, the Bose-Mott insulator and the superfluid, are kind of extreme opposites of one another. In the superfluid, you have kind of coherence in momentum space. In the Mott insulator, you have a sort of localization in real space. They're extremely different states, and indeed, they're different phases of matter. They're not smoothly connected to one another. Like all quantum phase transitions, to go between one phase and the other in equilibrium requires some kind of very non-smooth behavior of physical properties. In fact, what we call critical singularities. The density will jump, for example, the correlation length diverges. The superfluid order parameter or the superfluid density will have some singular behavior at the transition. And like all phase transitions, one of the reasons we like it is they have a certain universality. Small changes in the model, as long as they preserve the two states, will not change the universal critical properties like exponents at those transitions. The Mott transition itself is kind of particularly interesting and special in some way because this Mott insulating phase here it has a nice way to think about it in terms of just the quantum state, but it does not involve an order parameter. There is no symmetry broken in the Mott insulating state. The insulating nature of it is a purely quantum phenomena. And for example, if you were to heat up the Mott insulator, there's no longer a notion that it's really a distinct phase of matter. It's just kind of a normal fluid. So this is maybe a similar thing in pictorial terms. Here's a kind of picture from Wikipedia of a quantum phase transition. So here we have the superfluid on one side and a Mott state on the other side, and separating it is a quantum critical point. If we were to heat the system up, there might be a classical phase transition between a disordered and an ordered state with some classical critical behavior in between. This quantum critical point has all sorts of nice properties. It has scaling, criticality, singularities, universality, all the things that theorists really like. This quantum phase transition in particular also is really a zero temperature transition. So everywhere along this line, as you vary parameters in the Hamiltonian, like the strength of hopping, for example, or pressure in some system, the system is remaining in a ground state. It's just that the ground state is changing. So there's no normal sense of a normal fluid in zero temperature, in the zero temperature boson-Mott transition. There's no entropy anywhere. Now, these are all done in the context, really those experiments were done in the context of ultra-cold atoms, where many atoms behave like bosons. But in electronic systems, we can also build sort of composite bosons out of electrons. In particular, there's a very famous one, which occurs in any semiconductor, which is called an exciton. An exciton is nothing but a pair of an electron and a hole a hole in the valence band, an electron in the conduction band. Because they carry an opposite charge, they bind together. They have an attractive interaction in a semiconductor, and you can think of it like a tiny hydrogen atom. Okay. There's a difference between an exciton and an atom, is that an atom can't decay.
Some particles of phase or state.
I'm sorry, was that a question?
No, someone just forgot to unmute their phone.
Someone forgot to mute. Okay. So on the other hand, an exciton is only a metastable thing in a solid. It can decay. The electron and the hole have opposite charge, so they can just annihilate. This electron can drop down to fill this empty state in the valence band. All it has to do is emit a photon. So that's kind of the thing. You can put a bunch of atoms in a trap or a box, and they'll just stay there. The excitons will decay away in nanoseconds. But still, you can study them. And a very nice context to study excitons is in these transition metal dichalcogenide materials. These are 2D materials. I'll show you some of them. So these are kind of analogs of graphene. In many of these materials, the conduction band edge and the valence band edge occur at the near the boundary of the Brillouin zone, these K and K prime points, just like they do in graphene. The difference from graphene is that these are gapped materials, so the band gap is something like 1.7 eV or something in these materials. It's a pretty big energy. That's how much energy it requires to excite a hole, an electron from the valence band to the conduction band. But these, just like any other semiconductor, they can form excitons. In fact, they form more strongly bound excitons because they're 2D materials. There's a lot less screening, various reasons like this. They also have very nice optical properties. In particular, it turns out that there are optical selection rules. So by, for example, exciting with right circularly polarized light in many of these TMD materials, you can selectively create excitons at one or the other of these values. If you use right circularly polarized light, you'll create an exciton over here at the K point. If you use left circularly polarized light, you'll create an exciton over here at the K prime point. In the last few years, the focus has turned from bulk or single layer TMDs to these twisted 2D materials. So we take two of these TMD materials, either which are two identical layers and twist them, or we take two slightly different layers. They're not necessarily twisted, but they have some lattice mismatch. Together, these two different materials will form some moiré pattern, which will modulate the properties of the electrons and in particular the excitons on the scale of this moiré pattern. We'll be talking about systems which of heterobilayers, so the two layers are actually different semiconductor materials with a particular type of band alignment, what's called type 2 band alignment. So generally the edges of the conduction band in the two materials are not at the same energy, and the same thing for the valence band. In a type 2 band alignment, the lowest energy electron states lie in one layer, and the lowest energy hole states lie in the other layer. So ultimately, the lowest energy excitons will be made from putting an electron in one layer and the hole in the other layer. So that's called an interlayer exciton. They're actually spatially separated, the electrons and holes, but they can still bind. They're not separated by much in these atomic scale bilayers. So there's a lot of complex physics here. You can imagine there are lots of different exciton states you could create. We can put our, even if we choose to put our electron in one layer and our hole in the other layer, we can choose which valley the electron can be in, which valley the hole can be in, what spin the electron can be in, what spin the hole can be in. And the physics is generally quite complex. They may also live in different regions of real space in this moiré pattern. So this is really something that needs to be sorted out kind of system by system to understand the nature of the excitons in it. I'm going to be talking about experiments on this particular system, which has this type 2 band alignment, WS2, WSE2. So here the electrons live in the sulfur layer and the holes live in the selenium layer. It's well known in most of these TMDs that the holes have very strong spin-orbit coupling, so there's really only a single spin state available to the holes. To the electrons, it's less clear, but one can separate out and study the different possible spin and orbital states, and these have really been studied heavily by, actually originally by my colleague Chen Hao, now 5 years ago. That's not going to be so important for this. So, I'm not so accustomed to thinking about excitons. Coming from the world of magnetism, we are really focused on equilibrium systems. But it's useful to have some understanding of how these experiments work. So typically, to study excitons, you have to create them. If you don't shine a laser on your sample, there won't be any excitons in there. If you shine a laser on it and wait, they will all decay away. So the way these experiments are done is some excitons are created by some excitation laser, and which might be called the pump laser. And it's usually excited here at some energy, which is quite a bit higher than the lowest energy excitons we're interested in, which are these interlayer excitons. That's for various reasons, partially just because the system absorbs better at higher energy. These higher energy excitons, they can decay and fall into the lower energy available exciton states. That happens relatively quickly because it can do that. These excitons can lose some energy by radiating off phonons with relatively small energy. So what you end up relatively quickly with is excitons that are sitting in their kind of lowest energy states, which are these interlayer excitons. Okay, a lot of complicated physics happens getting the excitons from the initial state where they're created to these lowest energy excitons. Fortunately, those lowest energy excitons stay around quite a while because to recombine, the electron actually has to transfer from one layer to another. They also have to radiate a lot of energy away. That's not possible to do via phonons. It only happens via photon emission. So that's kind of a slow process. So this is a way you should think about what's happening. There's some excitation, which is kind of an incoherent process that eventually gives rise to these lowest energy excitons. And we're trying to watch what they're doing while they're still around. So in the moiré system, the additional element I mentioned is the excitons actually have preferred places to live in real space. So you can think that they experience a potential. The simplest way to think about this is there's just some modulation of the band gap in the semiconductor. In some regions of the moiré pattern, the band gap's a little bigger. In other regions, it's smaller. The excitons have lower energy in the region where the band gap is smallest. Okay. So this is a kind of semiconductor calculation of that, actually for a different system, but it's similar for all these moiré systems. So now I want to show you some experiments. This is kind of the first generation of experiments like this from Chen Hao's group. What they do is they vary the intensity of a pump laser. So basically, the stronger the pump laser is, the more excitons are created. What's really happening is they're creating excitons at a constant rate via this pump laser, and they decay away by emitting light. And there's some balance. The more you pump, the higher the steady state density will be that balances the decay and the creation. And so it's kind of a nonlinear process, but the higher the pump intensity, the more the density of excitons. What they measure is the intensity of photoluminescence. So every time an exciton recombines, it emits a photon. And the photon will have the energy, it carries the energy that the exciton had beforehand. So when there's a low density of excitons, you primarily see emission at this energy around here, which is just the exciton of this lowest quasi-stable exciton. As you vary the pump intensity, it shifts a little bit. What's happening is you're adding more and more excitons to the system. They're all sitting in the smallest well, kind of the lowest energy state of this periodic moiré potential. As you add more and more, at some point, something interesting happens. The intensity kind of largely drops away of this first line, and a new line appears at a slightly higher energy. it's good to have an idea of the scale. So the exciton energy itself is quite big. It's about 1.5 electron volts, and the intensity of the line shifts by a few tens of millivolts. So what's going on in this experiment? I should say, so what's really being measured here is not the full intensity of emitted light. So they do something a little more clever than this. What they do is they, in addition to a overall intensity, which they're just increasing smoothly, I0, that's the vertical axis here, they add a small modulated intensity. You should almost think of it as DC. It's just done at very low frequency in order to be able to extract a different signal. So as I increase the intensity a little bit, I will increase the density of excitons slightly. And now I can probe the change in the photoluminescence just caused by this probe light. And so that's what's actually plotted here. So it's sort of the derivative of the photoemission signal with respect to intensity. So what's happening here is that I add more and more excitons. Every new exciton I add is emitting at the energy of an exciton. At some point, when I add more excitons, they start emitting at a slightly higher energy. And it's quite abrupt, this shift, and very reproducible. And the picture you should have is that when I get to this point, I've actually filled all the wells of this moiré potential. When I add one more exciton, I have to actually create a different state. I have to make a doubly occupied well. I have to put two excitons in one well. If you think of this boson-Hubbard model, that costs an extra energy, a repulsive energy between excitons, and that's what this energy shift represents. So this experiment seems to show an abrupt change of behavior. Anything abrupt is a sign of a phase transition. And it seems to be in accord with the picture that when I reach the point where I have one exciton per well, this is a Mott insulator of excitons in which there's a gap. That's a kind of characteristic property of a Mott insulator. There's a gap to adding another particle. I found this really amazing that you could see anything like this in a highly irradiated two-dimensional material like this. And the sort of interesting theoretical questions are, how much is this actually like the boson-Mott transition that has been studied for decades in equilibrium systems like cold atoms? So this is very much a non-equilibrium system. If you turn the lasers off, all the excitons will go away. It's constantly being illuminated by a pump laser, which is generating incoherent transitions. In addition, energy is constantly leaving the system as light is emitted. So this is a highly non-equilibrium system. And we can ask, do any of our ideas about the Mott transition really apply in such a non-equilibrium system? I'll talk a little bit about theory now. So with Tessa and Zenhao, we started to try to ask this question, starting from this kind of basic Hubbard model. So here, this is pretty much the same Hubbard model that Fisher et al. Wrote down in the 1980s. It's a Hamiltonian. So there's we have some hopping between sites I and J on a lattice with some hopping matrix T. We have a Coulomb repulsion between bosons, and we have a chemical potential. Okay. An important difference from the usual cases, this chemical potential is actually very large and positive for the bosons for these excitons. An exciton costs an energy of like 1.5 eV to create. Okay. So because it's such a high positive chemical potential, the equilibrium system or the ground state of this Hamiltonian just has no bosons in it. So it's very boring and trivial. To make this interesting, we need to include the fact that we're irradiating this system of bosons with a laser. I should say, just for now, I talked a bit about a bunch of the actual physics of these exciton states, but to ask these questions about the Mott transition, et cetera, I'm going to really simplify the picture. Let's ignore the fact that the excitons will have spin, they have valley, and just try to treat these non-equilibrium aspects. So there's a pretty nice, well-established formulation to study non-equilibrium systems. which is open quantum systems, which is called the Lindblad equation. So this is an open quantum system because these excitons are strongly coupled to the electromagnetic field. They're constantly being created or annihilated. So to study it, we should study really not eigenstates of this Hamiltonian, but rather the density matrix. So this Lindblad equation describes the evolution of the density matrix, and it involves two terms. One is kind of this familiar one that you have just for quantum evolution of the density matrix in a closed system. The second one might be less familiar. These are called the jump operators. So they don't act on the density matrix like a commutator. They act with this kind of funny structure. Basically, what this jump operator represents for each choice of these A's and B's here in this Lindblad term describes a particular type of transition that the system can make. For example, a photon can be absorbed and an exciton created, or a photon could be emitted and an exciton annihilated. Indeed, sort of microscopically, the way this Lindblad equation is derived is by including coupling of our system to an environment. Here, in this case, what we want to think about is that these excitons are coupled to the electromagnetic field. Now, the electromagnetic field at these energies has a long wavelength, actually, and the wavelength is much longer than the Moiré period. And because of that, we should think that the electromagnetic field is coupled almost uniformly to the exciton creation and annihilation operators. So it's just the coupling of the electromagnetic field of the laser to the electrons and holes in the semiconductor would have a form like this, where for example, this term represents annihilation of an exciton and creation of a photon. So these R's and R daggers, they kind of live in the Hilbert space of the electromagnetic field. And these little b's, I call the sum of all the little b's big B here, they live in the space of the excitons. So there's a kind of standard derivation. This is the theoretical part of the talk. I apologize to the experimentalists if it's a little heavy, where one basically traces out the environment using a kind of standard Markovian approximation and obtains this Lindblad equation. And the way you do it is you need to know the spectral correlation of these R and R daggers, which are called the Bath operators. And we need to decompose these, the system operators, these big B's, into what are called eigenoperators of the system Hamiltonian. So basically, these are the operators that change the energy of the system by a definite amount. So the reason we want to do this is that basically a given type of photon, which has a certain energy, will only create transitions between states of the system that differ by that energy. So this is kind of, this approach is a way to take into account energy conservation in the total system of the subsystem and the environment. So with this technical procedure, once you find these eigenoperators, then you can build the Lindbladian Lindblad equation in the out of him, and it takes this form. So this is written in the interaction picture. So if we go to the interaction picture, basically it's like conjugating rho by the time evolution operator of the original Hamiltonian. This term drops out, and we're left with only a set of jump operators. The important thing that occurs here is that all the information of the bath ends up subsumed into two types of coefficients. There's a gamma, which is a kind of decay rate. So this represents processes in which bosons are annihilated and photons are emitted, and I, which are absorption processes where photons are absorbed and bosons are created. And these two coefficients actually they measure different properties of the spectra of the bath. So Unfortunately, to carry out this procedure, which is really a standard one, you can find it in books, for example, on quantum dynamics. It's a hard thing to do. You have to actually find these eigenoperators. And in general, for our Bose-Hubbard model, we don't actually know how to do it. So to make progress, we made a kind of simple theoretical assumption. What we did is we took a sort of mean field approximation for the hopping. We basically replaced the nearest neighbor hopping of bosons on a lattice by an all-to-all hopping. So a boson on site I can hop to site J, any other site on the lattice, with some hopping amplitude that's divided by the number of sites. So this is something very familiar if you've studied theory of phase transitions. This is kind of like studying an infinite dimensional model or sometimes called a spherical model. Generally, this will give, for equilibrium statistical mechanics, this gives a natural mean field approximation to critical behavior, and it does a good job in understanding the phases. It's actually the way that this original Bose-Hubbard equilibrium phase diagram is calculated in such an approximation. So once we make this approximation, it's really only an approximation to the tunneling, to the hopping of bosons, then we can actually solve this hard problem we need to build the Lindblad. And the reason is that this Hamiltonian, once we have done this, has a very high symmetry. If every boson can hop, if a boson can hop from one site to any other site, this has a permutation symmetry. There's no difference between any particular site on the lattice. So we can actually permute any pair of sites or any set of sites on the lattice. And that's a huge symmetry group. Anytime we have a symmetry in quantum mechanics, we can use it to simplify calculations. So basically what we do is now we can drastically reduce the space we need to study the density matrix by studying only states that are symmetric under this permutation symmetry. So in general, we have states like this where on my lattice, I have N0 sites that are empty, N1 sites with one boson, and 2 sites with 2 bosons, et cetera, up to NM sites with M bosons. Okay. We can make M as big as we want. Just put in some cutoff for the maximum number of excitons on a site. One can construct these eigenstates of this form analytically or numerically for general cases. And once we do this, we can actually completely build the density matrix in this basis of symmetrized states. The advantage of doing this, so the hard work is kind of building this basis of states. Once we do it, the Lindblad equation becomes something kind of simple. It looks just like rate equations. So you can see that in this basis of states, it looks diagonal. That means we can interpret the coefficients. Anytime you have a diagonal density matrix, the coefficients can be interpreted as probabilities. There's still coherent quantum effects inside each one of these states. These are kind of superpositions in which bosons occupy different sites of the lattice coherently. But the coefficients are really probabilities. And so the Lindblad equation just becomes a kind of master equation for these probabilities. So the probability of finding a state with this particular combination of n bosons is related to various other probabilities by this rate equation. Basically, these are the I terms represent excitation, where I start from a state with a certain number of bosons and I add one more boson. I would increase the number of singly occupied sites or the number of doubly occupied sites. Will depend where that boson gets added. The gamma term represents situations where I remove a boson. So if I have 20 singly occupied sites, I would create a new state with only 19 singly occupied sites, for example. Okay, let's leave that technical part behind. Trust me that we can really do this, and we can do this in varying levels of detail. So there are a few exactly soluble cases. So one case is where there's no hopping at all. So that should be sort of the best case scenario for getting Mott insulators. If there's no hopping, clearly we should we won't have a superfluid state, but do we have a Mott insulator? That's already not so obvious because it's not a system in its ground state. Remember, the equilibrium system at non-zero temperature, if we had a non-ground state but thermal state, there would be no Mott insulator. Another limit we can study is the hardcore bosons. So that means we never allow anything more than empty sites and singly occupied sites. And then we can also do things where we allow, for example, up to 2 bosons per site, but not 3. In this case, we can't really solve it exactly, but we can do it pretty much numerically exactly. So in all these cases, we can just find the steady state solution to this Lindblad equation. We just solve for the limit where rho dot equals 0 and find a stable solution, which turns out to be unique. So once we have the solution, we have the density matrix, we can calculate anything we want. So for example, we can calculate as a function of here the strength of the pump intensity divided by the decay at various different parameters. So there's some particular chemical potential. The important thing to look at here is the ratio of Hubbard interaction to hopping. So here it's quite large. So this is a very strongly repulsive system. And what's plotted is the average number of bosons divided by the total number of sites. And what you can see is that, and these are curves for different sample sizes. So as the sample size goes to infinity, so the thermodynamic limit, we need a large system limit to have a real phase transition. We see a step-like form here. So it really, for a certain range of intensity, we just have really, in the thermodynamic limit, no bosons in there. They're actually always bosons, but they don't scale with the size of the system. Oops. When we increase the intensity beyond a certain point, there's a jump, and the number of bosons moves into this region where it's 1 per site. So this is like the kind of singly filled boson Mott insulator with 1 exciton per site. At higher intensity, we'll reach another state where we have 2 bosons per site. If you do this for somewhat larger hopping, you see something similar. Again, you have these kind of quantized plateaus. So the quantized plateau here is a signal of a Mott insulator. But in between, we find these kind of smooth transitions between them. The smooth transitions are sort of indicative of what you might see in the superfluid phase. And in fact, if we plot this same data on a density plot, so here I'm plotting vertically the strength of hopping over U in some dimensionless form, and horizontally is basically the strength of the pump intensity. You can see rather clearly these 3 incompressible regions, 0, 1, and 2, where we have really no bosons per site, 1 per site, 2 per site, and in between some kind of compressible region where the density varies smoothly. So this is very much analogous just in terms of particle number to what occurs in the equilibrium problem. Okay. So a question you can ask is, in these smooth regions here, where the density is actually varying continuously, or in here between 0 and 1, that's like in this region here, is that a superfluid? So the way we look at this is by asking about whether there is Bose condensation. So in particular, we can study this property, which is sometimes called off-diagonal long-range order. We look at the correlation function of a expectation of creating a boson at site I and removing a boson at site J. Of course, when I equals J, this is just the number of bosons on that site. But when I is not equal to J, this is only non-zero if there's some coherence between the site I and site J. So this, to get a non-zero value in the thermodynamic limit, this sum needs to scale like n squared. And so this only happens when basically arbitrary pairs of sites, no matter how far away they are in the lattice, are coherent. So this is kind of a way to measure basically the square of the superfluid order parameter, or the condensate. So here are some line cuts here at small hopping, so large interaction, and here at strong hopping, so relatively weak interaction. You can see for weak hopping, as you scale up to larger and larger system sizes, in most places, this condensate order parameter gets weaker and weaker and really extrapolates to 0 in the thermodynamic limit. But there's some narrow regions where it extrapolates to a non-zero value. On the other hand, at strong hopping, you get a condensate over a large range of hopping, a large range of intensity versus decay. And here's a density plot of that. So this in the thermodynamic limit should be 0 inside the Mott phases if they're like the usual Mott phases, and indeed they are. And this non-Mott region does indeed appear to be a condensate in this picture. So these two features look really a lot like the usual Bose-Hubbard model zero temperature phase diagram. But I want to emphasize that it's actually quite surprising it looks like this because, as I said, this is a very non-equilibrium system. And in fact, all these things are coming out of a highly non-equilibrium density matrix. That density matrix really does not look like e to the minus beta h for any Hamiltonian and any temperature. It's something that's really determined by the balance of these excitation and decay processes. And in particular, one way to see the difference is to look at the entropy per boson in this exciton system. So in the usual equilibrium Mott system, our condensate phase diagram might look a lot like this. The density phase diagram would look a lot like this. But this big region in here between the Mott lobes, this is a condensate. It's a macroscopic occupation of a single quantum state. And because it's one quantum state, it has no entropy. But that's not at all true here. The entropy per particle is actually finite and large everywhere within the non-Mott region. And in fact, it peaks nicely at these quantum phase transitions. So this is kind of a direct indicator that there is a lot going on here that's different from the equilibrium system. I think I'll skip this part. We started looking at critical properties. One can start thinking about these type of theoretical questions. I want to summarize what I said so far and then come back to the experiments a bit and talk about some more physics of the excitons. So I came into this asking the question, does this out of equilibrium system, these driven excitons in a moiré lattice, is it even possible for this to exhibit a Mott phase or a superfluid phase? And surprisingly, the answer, at least within our model, is yes, but that these phases are really fundamentally different from their equilibrium phases. For example, this entropy is very, very different from what would occur in the original superfluid insulator transition. So, experimentalists in the audience probably fell asleep for some part of that, and I wouldn't blame you. Got a little technical. It's always good to have a little sanity check at some point and ask, what does all this actually tell you about experiments? Well, the honest answer is there's not, at the level that we've talked about so far, there's not that much in detail to compare against. This is kind of the main bit of experimental data. Again, I showed it to you before. This is the photoluminescence spectra as a function of pump intensity. One can convert it to this figure on the right here, where instead of pump intensity, they've used some experimental method to replace that by the density of excitons that are present in the steady state. So that's not a linear function of the pump intensity, but they can determine that by some photon counting method, basically. So they look pretty similar. What you can see is that there's a small shift in the photoluminescence frequency, and there's a jump here in this signal, and in particular, the intensity drops away from the low energy peak and comes back out of the high energy peak. And there is actually, when you plot it this way, it's kind of clear that there's some overlapping region where both signals are present. Again, this lower peak should think of as emission from single excitons, and the upper peak is emission from double excitons. How do we compare this with anything we calculated in this model? Well, kind of the vertical axis here, increasing density, has something to do with our horizontal axis where we're increasing intensity. So I should say that there's no obvious mapping between the intensity in our calculation and the pump intensity. I think probably a better way to do it would be, and the reason is that the pump intensity, the way it actually works is through some absorption of higher energy states. And then there's some complicated process of these higher energy excitons relaxing into the interlayer excitons that we care about. So that physics needs to be somehow encapsulated in the model. We believe it's correct to model it via this Lindblad term. But one could try to calibrate this by replacing this horizontal axis by exciton density. Basically down here, it's very small. It's increasing here. It's plateaus for a while. In this region, we have N1. This red line is showing the number of singly occupied states. So there are a lot of singly occupied states. They can all emit. They would create intensity at this energy, and there are almost no doubly occupied states. But as I start passing this point, I move into this region here. The number of singly occupied states decrease and the number of doubly occupied states increase. That would represent this kind of overlap region where the intensity is dropping from the lower peak and showing up in the upper peak. And when I get beyond this point, I have only these doubly occupied peaks. Okay. So qualitatively, it seems to describe this physics. We don't feel comfortable trying to make it quantitative at this point. So what do we really learn from this theory about these experiments? I'd say it's more conceptual than quantitative. This tells us that the stable Bose-Mott state can actually exist under illumination, and we qualitatively see this, can understand this trend of filling singly occupied and developing doublons of excitons. But if I'm really honest, in fact, we could describe most of this physics in the limit where there's no hopping at all. So there are a number of interesting issues that arise when you start thinking a little more deeply. I want to talk about one of them. In particular, I'm not going to talk about the first two, really. I'll just mention. We've really considered only the transitions, the kind of dissipative terms in the Lindbladian that arise from coupling to the electromagnetic field. There can be additional ones which have to do with, for example, coupling to phonons. One of the nice things that's really interesting about this system is that here I've talked about experiments where you have a neutral semiconductor. There are no carriers in equilibrium, and you just create them with optical excitation. So you always create an equal number of electrons and holes. But you can take the very same sample and gate it and create an excess of holes or excess of electrons, and then excite excitons on top of it. So there's a lot of interesting physics associated with the combination of unpaired electrons or holes, so fermions, and paired electron-hole pairs, bosons. So those are all interesting things. I won't say anything about them now. What I do want to say a little bit about is this kind of valley degree of freedom of excitons. So I mentioned at the beginning that these TMD materials are a lot like graphene. They have kind of two valleys at the K and K prime points of the hexagonal Brillouin zone. You could think of building excitons from each of these, and it's a bit like having a spin flavor of excitons. These valleys are quite robust. And in particular, you can kind of tell by looking at the radiation that is emitted what type of exciton you had. So an exciton that was at the K valley, when it recombines, emits a right circularly polarized photon. And if it were at the K prime valley, it emits a left circularly polarized photon. Similarly, if you irradiate with right circularly polarized light, you preferentially generate the K valley excitons, and vice versa with left circularly polarized light and the K prime valley. So this is a more recent paper, also from Chen Hao's group, where they make a small twist on this experiment. Again, it's the same sort of protocol. There's a strong uniform laser that's on all the time, and then they add a modulated laser. This modulated laser, the uniform laser is linearly polarized, so unpolarized. The modulated laser is circularly polarized, and it can be circular, either right or left polarized. And then they measure the emitted photons with either right or left circularly polarization. And they look at the change in the emission of right and left circular polarized light due to this polarized pump. So I want you to focus on these are too complicated. I want you to focus on the right-hand panels here. So this is at a very low excitation density. So only 3% of the moiré potential is filled with excitons here. The black line measures the intensity of right circularly polarized photons when I generate that are generated by a small probe field, which is also right circularly polarized. The red line is the intensity of left circularly polarized photons that come out when I generate with right circularly polarized light. And at these low densities, you can see that they're actually almost the same. So that might be a little weird. I add K-Valley excitons, and the light that comes out almost looks like it comes equally from K and K prime Valley excitons. And what it tells you is actually that there's a pretty fast conversion between K and K prime Valley excitons in the system. Okay, and that's known to be the case. What's interesting is that when they go to much higher filling, so this is a filling above 1 exciton per site, it just becomes dramatically different. As you saw, there's a second emission peak that occurs up here. So that's this peak associated with decay of doublons at this slightly higher energy. That represents the interaction between a pair of excitons on the same site. But you also see this dramatic difference. The emission of excitons with the same polarization as the pump is enhanced in the lower line, and it's reduced with the opposite polarization. So this is indicative of some valley physics, kind of spin physics of these valleys. And there's kind of a simple picture for it, which is kind of fun to explain. So this only occurs in the region where we have more than 1 exciton per site. So here's a kind of very random, very abstract schematic. We have the moiré lattice, so the sites here are the minima of this moiré potential. And in every site here is occupied by at least 1 exciton. I'd make the K-Valley excitons blue and the K-prime Valley excitons orange. And there'll be, since the density is bigger than 1, there'll be some sites that have both a K and a K-prime Valley exciton on them. They're a doublon. It turns out that you cannot create doublons of 2 excitons with the same valley. That costs much too much energy, and those don't occur. So now one has this system that has, some concentration of doublons in it and a bunch of single excitons, and you irradiate with a little right circularly polarized light. So this is going to always add a K-Valley exciton. So that K-Valley exciton can only go on the K-prime Valley sites because, as I said, you can't form a double exciton with the same valley. So now, once I formed this doublon, this extra doublon, it can do something. It could stay around, but it could also decay. The doublon could emit a photon and leave behind and since it has no net valley, it could leave behind either a K-Valley or a K-prime Valley exciton. So if you think of the net result of this process, because I added a K-Valley exciton, it always has to go in and change the state of a site that had a K-prime Valley exciton. So some fraction of the time, I will end up with a doublon and 1 less K-prime Valley exciton. Some fraction of the time, I will end up with a K-Valley exciton instead of a K-prime Valley. And some fraction of the time, I'll end up with the original K-prime exciton. So since this bottom choice doesn't occur 100% of the time, the density of K-prime Valley excitons will be decreased. There's some chance that I converted a K-prime into a K exciton, so I'll have increased the density of K excitons, and the number of doublons will increase. So these last 2 statements are the reason why the photoluminescence of K-Valley excitons increases and the photoluminescence of K-prime Valley excitons decreases. So you can see, you can understand this from the existence of this valley degree of freedom, but I can kind of understand the whole thing in a single site picture. What is really intriguing in these experiments, which I field we don't understand at all, are indications of magnetism. So in particular, ferromagnetism. In these pictures, I've drawn, just some random arrangement of K and K prime valley excitons. So ferromagnetism isn't like that. If there's some interactions between excitons on nearby sites, in some way, they might choose to align either ferromagnetically or antiferromagnetically. When they do that, they start acting collectively. There would not be some random arrangement of valleys of these excitons, but they could adopt some type of ordered state. And it turns out there are signatures of this type of ordering in this experiment. There are several, but what for me the most striking thing is what I show here. So here they're showing this asymmetry, basically the difference between this black and red curve, as a function on the horizontal axis of the energy of the emitted photon. But the vertical axis is a function of is the applied magnetic field to the system. And this is being done at the region of similar to these experiments, slightly above 1 exciton per site. I don't understand anything in detail about these plots, but what you can see just by the naked eye is that there's an effect on the intensity here. So this is this enhancement of this asymmetry. It's changed dramatically by application of a magnetic field of just a few millitesla. Okay, so if you think about how a magnetic field acts on these excitons, the excitons, they're electrically neutral, so there's no real orbital effect on the exciton. They carry spin, so there'll be some Zeeman coupling. They carry an orbital angular momentum because there's strong spin-orbit coupling of the hole states in these semiconductors. But all that physics is sort of coupling on the scale of a Bohr magneton to this magnetic field. And so an application of a millitesla magnetic field to a order Bohr magneton magnetic moment is changing the energy of an exciton by an energy of a few millikelvin. So whatever is going on in this system, there is absolutely no way that it's as cold as at temperatures of order millikelvin. In fact, it's probably very hot because it's being irradiated constantly by these lasers. It's extremely dramatic that a magnetic field of this scale, which is changing energetics by such a tiny amount, is having any effect on quantity like this that you measure optically. So almost the only way to rationalize it, the only way I can really think of, is that there's some sort of amplification of the effect of a very small magnetic field. And this is indeed naturally what occurs in a ferromagnet. When you have magnetic order, each individual magnetic moment doesn't act independently, they act collectively. And it's like you form a giant macro spin whose spin is the size of the number of magnetic moments in a domain. And the appropriate energy scale that should be compared to temperature or some measure of energy that's around is the number of those moments in the domain times the microscopic scale. And that would allow this very tiny field energy to translate into something that could actually affect the system. And indeed, these same types of magnetic fields actually are known to affect ferromagnetic states of holes in these very same TMD materials. So this seems to be some clear indication of ferromagnetism. We don't really understand the mechanism of it, but it's something interesting to think about. I think I want to stop there and appreciate your time.
Thank you very much. Yes, it's very, very interesting. So I'm sure that, quite other few questions, like a lot of people are here. So let me ask you, so if you think, somehow such a small field can induce potential magnetism in this dynamic system, I mean, it should, definitely be, directional dependent, right? You should expect, the sort of because a simple ferromagnet, like what you described earlier, should be strongly dependent on which direction of the field you apply. And do they see any directional dependence of the field, optical response?
My understanding is they've only done the field measurement with a field perpendicular to the plane.
Okay. Yeah. I mean, the other question I have is that if you think about a typical Mott insular, like the case of cuprous, right? I mean, that's associated with symmetry breaking. But in your picture, I mean, of this sort of a changing density induced Mott insulator. So what is really happening? You said that entropy does not change, right? What is really happening between these sort of two states? Why is it suddenly, it's a particular doping that you induce sort of a Mott state? I mean, I'm sort of an experimentalist, right? I want some sort of a simple picture so I can understand.
Yeah. So I think, what happens is that it's kind of a self-consistent process that the Mott state is. So it's throughout this phase diagram, in some sense, the temperature is actually changing. Normally we think about a phase diagram at constant.
Right, zero temperature. Yeah, zero temperature.
But that is not really what you're doing in these experiments. You're varying a ratio of. You're varying some pump intensity, and the system has its own means of dissipation. And it can happen, and that's kind of what happens in the Mott region, that it finds itself a localized region of Hilbert space where it is naturally in a small number of quantum states. And the entropy there is very small. Once you get into the region where it's not Mott, and it takes a while to get out of that, because there just aren't available excitations to create, then it forms a lot of entropy.
I see.
So
spins are not. I mean, spins are not involved, right, in this sort of picture, right? There's no.
All the calculations we did had no spins in them actually. So yeah, we have done some similar things with spins, but I think the basic physics is not that really. Yeah.
Okay, involved. Okay.
Yeah.
Andreas.
Yes, I had a short question regarding your results and the comparison to the experiment. So in your calculations, you nicely found these two steps.
Yeah.
In the exciton density, right, as a function of pumping, and the second step you could connect to the experimental finding. With this additional intensity at this higher photon energy. But what about the first step?
Yeah, I guess
is there any indication for the first step?
Not really. I mean, the thing is, so this step is, you see this step when plotting as a function of intensity, and in intensity in our model definition. Okay. The problem is I don't think our model of intensity really maps onto pump intensity. If you were to change this axis to exciton density, as soon as you get to a non-zero exciton density, we're already in this upper region. So that would correspond, the whole curve here on the right-hand plot would kind of correspond to starting here.
So you're arguing
you would see this. There's
the
a kind
intensity
of
actually goes a little bit up, which is
that you kind of see
the slope
right?
that you see, but the step you cannot describe because you don't have excitons at this gamma below 1.
Yeah, so in the left-hand plot, maybe some of that physics is there. It's a little bit deceptive because this is a log axis.
I see.
Actually, it is staying at a low density for quite a while, but and the intensity here is quite weak. So maybe I just don't feel comfortable to make it quantitative, but yeah.
I mean, so in your picture, I mean, does correlation play an important role or plays no role?
Correlation on a single site definitely plays a role. If there were actually superfluidity like we have in our model, that would certainly play a role. I think there are no indications of it actually in the experiment. I think the only experimental indication of correlations is really these ferromagnetism.
Right.
That I think is really, it's very, very hard to explain without some correlation physics. And they're I didn't show you all the data because it's a little hard to explain. But there are definitely indications of correlation physics when you start looking at the valley kind of pseudo-spin of the excitons. That's where we can start really seeing things. But you can say, arguably, depends a bit what you mean by correlation. But
sure.
We usually think of Mott physics as correlation, but a lot of the Mott physics is single-site physics. So,
I see. Yeah, so I mean, it's quite interesting, right? Basically, you're arguing that this purely dynamic process can be approximately interpreted by sort of a semi-static picture, right? Well, or close to it. Yeah. Yeah, great. Yeah. Okay. Are there any other questions for Leon? Okay. If not, yeah, I mean, it's fantastic. Yeah. Thank you, Leon. Yeah.
My pleasure.